Hello, Justin. Sorry, John Berg. Sit here. I'll make my way out. Go around there. I'll sit behind you. Okay. Sorry about that.
All right, good morning, everyone. Let's get started. Welcome to the class. This is a new course in data science. It's optimization for machine learning, and my name is Jiaming Liang. I'm a new assistant professor in data science and computer science. Thanks for coming, everyone. Okay, so let's first talk about the logistics of the class. Our meeting is on Tuesday and on Thursday during this time slot, and this is a building we are having the meeting, Highland 203. And I'm going to be your instructor. Our teaching assistant is Lin Zhang here. Basically, for all the course materials, announcements, assignments, and homework, all the gradings will be appearing on Blackboard. And we will also use my home web page for additional reading assignment. And so you can check both regularly. And we have 2 office hours. The first one is Wednesday from 4 to 5 p.m. This is in my office, Whiteman's Hall, just across the quadrangle there. It's Whiteman's 2403. And another office hour is by our TA Lin. This is on Friday, same time, 4 to 5 p.m. And this is in the student room for data science in Whiteman's Hall, 1219. Sorry, I was running just now to bring my computer, so I'm not speaking very well now. So this is the basic information of myself. As I said, I'm a new assistant professor in data science and computer science. And this is my office. It's also the place where I hold the office hour. And you can reach me by sending me an email to this address. So briefly about my background. I got my PhD in operations research from Georgia Tech 1 year ago. And during the last academic year, I did a postdoc in computer science department at Yale University. For my research interests, basically I'm interested in optimization algorithms. As you can see here, I list a few topics: length-smooth optimization, stochastic optimization, and many others in optimization. Here's another chair if you want. And I also do research in sampling algorithms. I will briefly talk about stochastic optimization and sampling algorithms in the end when I talk about the applications of optimization in machine learning. So basically, that's what I do. Everything about algorithmic design and analysis. I'm very interested in that. You can reach our TA Lin by this email address. And again, her office hour is on Friday afternoon. Okay, so talking about the grading, we will not have final exams. I guarantee you there's no final. We will just have one take-home exam that's going to happen it's in the week before the fall break, so October 10th to 12th. That takes 20% of the total grade. And we are going to have 5 problem sets. Each takes 10%. So in total, we have 50%. And the rest, 30%, is going to be a project. So instead of having a final exam, we will have a final project. For the project, it's graded in the 3 elements. So first of all, you need to have a proposal by November 7th. This will take about 10%. And the presentation is the last meeting of the class, December 12th. It's also 10%. And the last 10% is the report. So you need to write a final formal report 3 days after the presentation. So you need to keep in mind of all these important dates. If you have anything happening before that, please tell me at least 1 week before so that we can prepare. Otherwise, if you miss any assignment, there will be zero grading for your assignment. So late submission is not accepted. Please be aware of this. We are going to use these 2 textbooks. The first one is by Amir Bek. This is first order methods in optimization. The other is by Yuri Nesterov, lectures on convex optimization. Both of them talks about convex optimization, and they both focus on first order methods. This is going to be the focus of this class, but we will also talk about more advanced methods like high order methods and second order methods. Basically, we just focus on first order method. I will talk about what first order means later on in today's lecture. In addition to these 2 textbooks, I also strongly recommend you to read the following 3 books. The first one is by George Lang from Georgia Tech. This is a book on first order and stochastic optimization method for machine learning. So in this book, he will talk about many interesting applications in machine learning by using both first order method and stochastic optimization approaches. And another book is a more recent book by Ben Rich and Stephen Wright. This is a optimization for data analysis. So this book focuses not only the method but also the applications more related to data science. And the last one is a review book. This is a survey book written by a bunch of people. And these 3 guys are the editors of this book. This is kind of outdated because this has been 12 years, but it has several classical results. For example, interior point method, which is a second order method, and like mirror descent, gradient method, subgradient method. All these are classical results, but they were the state of the art at that time. But nowadays, after 12 years development, more and more advanced algorithms have been designed, and we will talk about some advanced algorithms. Okay, so here are the tentative topics of this class. First of all, we are going to talk about the interesting applications of optimization in machine learning, and we are going to cover the basics, which are convex analysis and also complexity analysis. Because we are mainly focusing on convex optimization in this class, but we will also cover 1 or 2 lectures on non-convex optimization, since it is very popular nowadays, like many optimization problems in deep learning are non-convex, do not guarantee convexity in real applications. And complexity analysis is another focus of the class, because this is the way how we examine the efficiency of an algorithm. We want to analyze how many iterations the algorithm will do, what is the computational complexity. So everything will be discussed in the complexity analysis. And after the introduction, we will move on to the basic results, the classical ones in first order methods. For example, the gradient method for smooth optimization, the subgradient method for non-smooth optimization, and also mirror descent, which is a variant of subgradient if you use different metric. And we will also talk about proximal gradient method. Basically, you can view the gradient method as in terms of a numerical analysis. In the language of numerical analysis, gradient method can be viewed as explicit schemes, and proximal gradient method can be viewed as implicit schemes. Usually, implicit schemes are more robust and stable than the explicit ones. So we will see the benefit of using proximal ideas. And proximal is one of the key ideas in the whole class. You will see proximal shows up many times, either in optimization or in sampling. So this will be the backbone of many modern analyses. We will also talk about the very famous algorithm, Nasarov's acceleration method. I believe some of you must have heard about this. Acceleration was one of the state-of-the-art algorithms used by machine learning people because this is the optimal result in convex smooth optimization. Compared with gradient method, which is suboptimal, this is optimal. So basically, this is faster than gradient method. And we will talk about what optimality means in today's lecture. The last topic of the basic classical results will be Frank-Wolf, which is also called conditional gradient. Basically, this is a projection-free method. Suppose you want to minimize some function over a convex closed set. Probably when you do gradient method or subgradient method, you need to do a projection onto the set. Because if you do a gradient step, you may go outside of the region. So because the constraint is a set, you want to go back to that region. So this is a projection step. A projection could be expensive in many cases. So the benefit of project-free or Frank-Wolf is that you do not need to do any projection. Your search point is always within the region. So this is a benefit. All these are classical results. They were developed, basically, most of them are developed in the last century. So, but these are oldies but goodies. There are some very useful results. We will also talk about advanced, more recent results in first-order methods. For example, the inexact proximal point method. This is a framework of many well-known algorithms in continuous optimization. I will give you concrete examples later, but just to name a few. ADMM, alternating direction multipliers of direction, ADM, alternating direction method of multipliers. ADMM for solving distributed optimization, and also some of the algorithms we mentioned before, like the proximal algorithm. Many variants of this one can be viewed as the instances of inexact proximal point method. And also, Nasav accelerated gradient is an instance of this one. And also for solving min-max set point problems, which is the core of, again, right, the generative adversarial networks. So to solve min-max optimization, usually we use Shapley-Polk method. Shapley-Polk is again an instance of inexact proximal point method. So this is a very powerful tool to design algorithm optimization. But we will also see the powerfulness of this key idea in sampling. So it also applies to infinite dimensional optimization problems. We will also see operator splitting for solving problems with composite structures, and also randomized block coordinate descent for huge scale optimization. And also we will see some recent developments in optimization. This is optimization in relative scale. This is some new notion. Some of you may have heard about strong convexity and smoothness. And there is a new notion called the relative strong convexity and relative smoothness. So this is the optimization method developed in that case for the new notion. And also we will talk about smoothing techniques. In real application, you may not have smoothness in many cases. So you may encounter some bad cases like objective functions where you have some kink. Right, here you have some kink. These are the non-smooth part. So to handle this type of non-smooth optimization, usually we want to use the smooth ones we have developed before, and this is the smoothing idea is to turn a non-smooth one back into a smooth one, but you need to pay some price, and this will be taken account into the complexity analysis. So these are the tentative topics that we want to cover for the advanced, more recent results in first-order methods. And after talking about first-order methods, we want to talk about some applications in machine learning. So these are the topics we will cover. We will first talk about non-convex optimization. All the results we mentioned before in first-order methods are for convex optimization. But for example, in deep learning and in many other applications like matrix factorization and sparse PCA and some formulation of SVM, they are all non-convex. So we will see how to design first-order methods for solving non-convex optimization with a complexity guarantee. The second application we will talk in machine learning is stochastic optimization. Many applications in machine learning can be written as a population risk minimization, but it may be difficult to solve because the population risk minimization has a form of expectation. Expectation means integral. Well, integral in high dimension is usually intractable. So we want to do some approximation. Usually there are two types of approximations, sample average approximation and stochastic approximation, SAA and SA. These are the two mainstreams in stochastic optimization. So we will study how to apply these two approximations to solve population risk minimization in machine learning, and how we can use first-order methods to derive the complexity bounds for all these approximations. We will also talk about distributed optimization. Basically, we will talk about ADMM method and some other first-order methods applied to distributed optimization. Distributed optimization is interesting because it has the benefit of preserving privacy. Sometimes you want to distribute your data into different into several data centers. Well, you want to keep all the data in a data center locally. You do not want to share your user information to other data centers, right? So distributed optimization will handle the problem about different privacy leak. So it does all the computation locally, but the difficulty is how do you communicate with other data centers? What is your data network? Is it centralized or decentralized? What is the efficiency if I use a decentralized network compared with a centralized network? And you need to design different types of first-order methods for different types of networks. And we will also discuss the complexity for solving optimization in a distributed fashion. We will also talk about manifold optimization. So all the applications and methods we talked about were in Euclidean space. But sometimes if you reformulate your problem as a manifold optimization, basically you can use the manifold, some certain smooth manifold to describe the constraint sites. For example, if you want to do eigenvalue decomposition, if you want to do eigenvalue decomposition, usually you need to, suppose you want to compute the maximum eigenvalue. Right, this is the optimization problem you want to solve for solving the maximum eigenvalue for a positive definite matrix A, and this is your constraint. But this constraint basically, so for example, in 2D, this is going to be a circle, right? All the v's such that the length to the origin is a unit value 1. So all the v's are on this circle. Or in 3D, this is a sphere, or in n-dimensional, this is a high-dimensional sphere. But this is a non-trivial constraint. This is a non-trivial constraint optimization to solve. But if you view this sphere as a manifold, then the first-order method can be translated easily into the manifold optimization setting. So we will see how formulation, how easy if you use the formulation of manifold optimization, you will solve the problem that which was difficult to solve before if you use Euclidean. If you solve the optimization problem in Euclidean space. So this is a way to transfer difficult problems, the normal difficult optimization problems into an easy one by using a different formulation. But we will see different developments of first-order methods in this setting. And finally, if time permits, we will also talk about reinforcement learning. Reinforcement learning is another interesting application of optimization in machine learning. Basically, in reinforcement learning, we are solving MDP, Markov decision processes. And there are usually 3 ways to solve it: policy iteration, value iteration, and linear programming. If you use policy iteration, some people can, with proper parameterization, you can parameterize all the policies by a vector. And this will give you makes the policy iteration to be policy gradient. So basically, you can translate all the first-order methods into using the language of reinforcement learning or MDP. You can translate them into policy gradient type algorithms. It's again a first-order method. So this is another application. And in the end, we are going to talk about some methods beyond first order. So we will talk about both second order and high orders. For second order method, one of the most famous algorithm in second order type is the Newton method. We will talk about Newton later on in this class. Well, second order methods are more difficult to compute, more difficult to handle because the computation here involves hashing information, right? Because hashing is a matrix, is more expensive than a vector if you do first order method. But the benefit is that the iteration complexity for second order method will be much cheaper than first order method. So there is a trade-off. Each iteration in second order will be more expensive, but you will perform less iterations. But in first order, you have more iterations, but each iteration is cheaper. So there is a trade-off. We will also discuss the complexity of second order method. And for higher order method, this is some recent development within 5 years. People have discussed about methods using higher order information. Basically, you want to do Taylor expansion into higher order polynomials. So if you want to do third order polynomial or fourth order polynomial, they will be viewed as higher order methods. Anything beyond second order is higher order. But since second order is more computationally expensive than first order, not need to say the higher order methods. So there is again a trade-off between the complexity, iteration complexity, and the computation you need to do for compute each iteration. So we will again talk about the complexity. But one thing I can guarantee is that the iteration complexity will decrease as the order you are using increases. So if you want to do first order, so this is the number of orders. So this is a number of order methods you want to do. And this is a complexity. This is the optimal complexity. If you want to do first order, then the optimal one will be epsilon to the minus 1/2. If you want to do second order, sorry, it's decreasing. So if you want to do first order, the optimal complexity for first order methods is epsilon to the minus 1/2. Epsilon is a tolerance. So if you want to find a point x, such that the function value of x is within epsilon distance to the optimal value. This is optimal value. For any epsilon greater than 0, if you want to find a point x such that the optimal gap is normal than epsilon, then this is your complexity. So basically, this quantifies how many iterations you need to perform to find such a point. We will give a more rigorous discussion about this one with definitions, mathematical definitions. But this is just to give you an idea. So this is the optimal complexity for first order method. Well, if you do second order method, if you use both the function value, the gradient, and the Hessian, if you use everything all together, then the complexity, the optimal complexity to find such a point for second order method is this much. It's epsilon to the minus 2/7. And this trend will go on. And basically, there is a theorem saying that if you want to find the epsilon solution for case order, the convergence rate is 1/k to the 3, let's say piece order. P is a positive integer number. So if you want to do piece order method, then the convergence rate will be 1/k to the 3p plus 1/2. K is the number of iteration. This can be translated into iteration complexity. Basically, so you basically want this one to be less than or equal to epsilon, and this implies the complexity is 1/epsilon to the 2/3p plus 1. So if you plug in p as 1, this is 1/epsilon to the 1/2. So this gives you this complexity for first order method. If you plug in p as 2, this gives you 1/epsilon to the 2/7. So this gives you the second order method optimum complexity. Does anyone? So is there any question? If you don't follow this part, it doesn't matter. We will talk more about it with more details later on. But this is just to give you an idea what the iteration complexity looks like if you do high order methods.
Sorry, I'm sure you'll cover this, but does that also apply to zeroth order methods, or is that just a different definition?
Yeah, it's a good point. Zero order method is when you only use function value. So you do not have gradient information. But usually, if you want to do zero order method, you will use function values to estimate your gradient. For example, this is like in numerical analysis. So if you want to estimate gradient f at a certain point x, I want to approximate by f of x plus h. Suppose I'm in 1D. Suppose this is just the derivative. Right. So if you do first a zero order method, we usually use two different function values to estimate the gradient at a certain point x. So this is either, but so again in zero order method, you will again evaluate some gradient information. So there is no pure zero method. You will somehow use gradient information. Any other questions? Okay, if you have any question, please do not hesitate to stop me. Okay, so that's all the topics we want to cover in the class, but if time permits, we are going to also talk about optimal transport. If not, that's all. But I will guarantee I will cover all of them. Okay, so in addition to homework and take-home midterm exam, we are going to have a project. Basically, this is to deepen your understanding of a particular topic, either in our class or something you are very interested in but not covered in this course. So basically, there are three types of projects you can do. The first is you can do a survey of any topic covered in this class or anything you are interested in that is related to our class. By related, I mean anything involves either first order method or higher order method or complexity analysis. Anything about optimization algorithms will be highly appreciated. And the second type of project you can do is implementation. So you can try to implement a type of algorithms covered in this class, while applied it to very interesting applications. The application could be something you found online or something in your own research or something you want to explore, but implementation does not mean trivial implementation. If you just implement something we covered in class and applied on some toy example, that doesn't mean a good project. A good project will be something that you can bring us some very interesting finding, I mean numerical finding. So by implementing a certain algorithm, you find something new, and that is something people have never seen. It may be some research topic. So this kind of implementation is what we look for. And the third type of projects you could do is purely about research. This can be any research idea that you came up during the course or anything related to your research, or if you want to apply any algorithms in this class into your research and you have something new, you can just present to us if you want. But this need to be something that is not very preliminary. So you cannot just say, hey, I have a good idea and I want to do this, but if you don't have the result, we cannot trust you. So you must bring us something solid. Just pay attention to all the timelines. So in addition to the 3 timelines we mentioned, the 3 points we mentioned before, there is another requirement on a short abstract. This is like a paper abstract. It can be just 1 paragraph. And this is not going to be graded, but this is a problem in your midterm, your take-home midterm. So during the 2 days of your midterm, you need to come up with an abstract, or you can do it even before that. So just try to think about the topic you want to do in your project as soon as possible. And this will be due during the midterm. But this is not be graded. We will only grade your proposal, presentation, and report. Is anyone clear about the projects?
Quick question.
Yeah.
Sorry to bring you back. You said you were probably going to cover optimal transport, maybe not. I'm actually interested in optimal transport. Just one of your thoughts on where optimal transport sits in the application areas of optimization.
Okay, good point. So I'm not sure if you know the application of GANs. Generative.
I do.
Yeah. So GANs basically you're playing with the distributions, right? Well, it's in a min-max, like a game theory type of optimization. And that min-max optimization is one of the most interesting optimization problems people want to solve because you do not minimize the primal, but also at the same time you try to maximize the do, right? The loss of one player is the gain of the other one. So you need to heavily use the notion of a primal do information, which is a key idea in optimization. And
So you consider that very frontier optimization research, essentially.
yeah, and another connection between optimal transport and optimization is that except the optimal transport, all the optimization problems we want to cover here are in finite dimension. So we are in Rn space, right? In Euclidean space, Rn, vector space. But the optimal transport, your discrete variable is distribution, which is an infinite dimensional object. So this is very different because you cannot compute, for example, you cannot compute the gradient exactly because this is an infinite dimensional thing, which is a probability distribution. You cannot describe a probability distribution exactly. So there are some intrinsic difficulty in infinite dimensional optimization compared with finite dimension. And so when we talk about optimal transport, if time permits, we will also talk about sampling algorithms, which is also closely connected to optimization. So on the one hand, optimization can be viewed as sampling in the limit. On the other hand, sampling can be viewed as optimization in the probability space. So there are very deep connections and very nice interpretations of each other from the other perspective. So this is a very interesting point. We will try to cover that. If not, you could try to do that in your project and present to us.
I'm told the professor from EES,
Oh,
so I'll talk to you more.
oh, sorry.
So that's
Sorry,
a
didn't
yes.
recognize this.
I approve.
Oh, sorry.
I will talk to you more about that.
Okay, so last thing about the logistic is the policy. So first of all, you are all encouraged to discuss homework, exam, either, and also your project with your fellow students. But when you hand in your homework, exam, and your project, you must write your own solution, your own code, your own final report. So you cannot share code, share the solution with others, but you can just discuss, write on whiteboard. That's totally allowed. Again, late submission is not accepted. So if you have anything emergency, or you have a job interview, or you have some family emergency, you can talk to me earlier, like at least 1 week before. Otherwise, we will not accept late homework submission. This is to the fire to the whole class, fairness of the whole class. We will encourage diversity inclusion in the class. So. And also, if you have any request, if you have any difficulty in following the class or any disability, please talk to me or talk to the disability office. And with that, we conclude everything about the logistics, and we will move on to the introduction of optimization. Before that, is there any question or any comment?
So I just have one question about the course material. So when we're covering stochastic optimization and non-convex, so you'd still say that convex optimization is the foundation that those are built on. So
Right.
you still need to understand that first.
Right.
Okay, just wanted to.
Yeah, that's why we do non-convex and stochastic optimization as applications. Right. We will prepare you ready for that with all the information, all the knowledge about first order methods. Any other questions? Great. So how many of you have taken any optimization courses before? Okay, yeah, we have quite a few. Okay, but don't worry, I will cover everything needed in this class, so it will be self-contained. You don't need to worry about that. So basically, this is the object you will see again and again in this class. This is the optimization program in general. So basically, we want to minimize an objective function f of x with respect to a set C. So x here, it's called a decision variable. This is where you make your decision. And f is the objective function, which is the one you want to minimize. And the C is called the feasible region. So you want to, by solving this optimization program, you want to find a point x that not only minimizes f, but also lies in the set C. So minimization and feasibility, they need to happen at the same time. And so C could be a set, or so C, okay. So usually we say the condition that x in C as a constraint. If you have many constraints, then you could have many conditions like x in C1, x in C2, and so on. So the general form of C is described by basically inequalities. Here, this h of x is an equality, but it can also written as an inequality, like h of x less than or equal to 0 and h of x greater than or equal to 0. So that's a different way of writing equality as inequalities. Well, basically, C is described by a bunch of inequalities. So this gi of x, each gi is a function. So gi could be linear, nonlinear, anything. But if it's nonlinear, of course, the problem will be more difficult to solve. The constraint will be more difficult to be satisfied. Okay, so here are some basic examples of the feasible regions, which is the set of C. So here are the examples where C is certainly a set, not described by inequality. They can be described by inequalities, but the simpler expression is by a set. The most basic one is when C is a ball. So C is a ball in a Euclidean space with L2 metric. So this is saying that the ball is centered at a point A with a radius r, and this is n-dimensional. 2 means L2 norm. So pictorially, this C looks like just a ball, and this kind of constraint, ball constraint, can be used in ridge regression. If you do the penalty method or Lagrange multiplier, you can put the constraint into your objective, which is a regularization term, right? So ball constraint can be used in ridge regression. And And another thing I want to mention in this class is that I will not only talk about all the optimization methods, complex analysis, but when possible, I will also mention related applications in machine learning. So this is how we advertise this course, right? Optimization for machine learning. We will not only talk about optimization, but also focus on applications in machine learning. But application is not the focus. Optimization is the focus, but they are motivated by applications in machine learning. So this is an application in machine learning. And another, so usually when we talk about ridge regression in machine learning, people can usually come up with lasso at the same time, right? And so the kind of constraint that you use in lasso is this type of sparsity constraint. Basically, you want to have an L1 norm regularization in your objective. And the constraint can be pictorially, it is this kind of octahedron. So this is again centered at the point A with radius r, but this is the metric is L1 norm. So I believe everyone knows about the L1 norm, right? So basically L1.
So what does the L1 norm mean?
Yeah, sure. I'm going to cover this. So L2 norm square means, so this is in Rn space. This is the first coordinate. This is a L1 norm. Basically, you sum up all the absolute values of each coordinate. And here's another one we are going to talk about is the infinity norm. This is a maximum over all xi's. Okay. And if you use a box constraint, so if the set C is a cube, so it's a cube in n dimension, then this is a box constraint. Box constraint basically means I want to constrain the magnitude of each of my coordinate. For example, this can usually be used in image problems because in image, for an image, let's say for a color image, each pixel has a value between 0 and 255. So this is a box constraint. The pixel value cannot be beyond this interval. And another example of a feasible region is a polyhedron. Basically, this is a polyhedron in n dimension. Sorry, I don't know the dimension of this one, but so this of course the one we present here is 3 dimension, but this can be something in high dimension, right? And this is usually used in linear programming. Basically, in linear programming, we want to minimize a linear objective subject to a linear constraint. So in linear programming, you want to minimize C transpose X. C is a vector subject to AX less than or equal to B. AX less than or equal to B, this is a more compact way of writing many constraints. So this can be equivalently written as A1 X less than or equal to B1, A2 transpose X less than or equal to B2, AM right. The A's are the the A's are the. So this is my matrix A. This is my X. This is my A1 transpose basically. And B, all the BI's are the elements of the B. The B is a vector, A is a matrix. So AX less than or equal to B something in one dimension, in 2 dimension, this can be any feasible region like this. So it's basically this feasible region here, but in high dimension, this can be a polyhedron. So these are the examples where C are certainly a set. But here, these are the examples where C can be described more explicitly by inequalities. So for example, here, this one is a negative Olsen. Negative Olsen in 3 dimension looks like this. Right, this is my X. This is my Y-axis, this is my Z. So it's just like a corner, right? And it's described by all the inequalities saying that all my elements need to be non-negative. And this can be used in, for example, non-negative least square or non-negative matrix factorization. Basically, I want to require all the elements either in my matrix or in my vector to be non-negative. And another example of C described by inequalities is a cone. It's a second order cone. So it looks like an ice cream. So sometimes people usually call it a second ice cream cone or second order cone or Lorentz cone. But basically, this is in 3 dimension. Look like this. This is the ice cream cone. And a typical application is in second order cone programming. This is beyond the scope of this course, but it is an interesting and important application in optimization if you want to do conic programming. And the last example we want to present here is the semi-definite cone. Basically, C here is very different from all the other examples because all the other C, the sites they are in the Rn space, right? They are a collection of vectors, they are sets of vectors. But here C is a collection of matrices. So here C is in the space of all the symmetric matrices. Here S denotes the n by n symmetric, the set of n by n symmetric matrices. And here C is the matrices that are also positive semi-definite. So this is another example of C, but this is for matrices. Well, a typical example of this one is in semi-definite programming. And the C here is also called semi-definite cone. So this is an example in when n is 2. So because when n is 2, your matrix looks like this. X, Z, Y, Y. Because this is in as 2 by 2, right? This is a symmetric matrix in 2 by 2 dimension. So, and so we are only interested in X, Y, Z. And that's why we can pictorially show the semi-definite cone in 3 dimensions, because only X, Y, Z matter. This Y is the same as the other off-diagonal Y. Well, all these examples are very important in conic programming, but they are not the focus of this class. Well, because in this class, we are mostly interested in first-order method. And all these methods, so these two are usually solved by second-order method. So that's why they are not our focus. But just to mention, these two are very important in optimization. And you can also do 3D printing for all these feasible regions. So this is a positive Olsen, this is an ice cream cone, this is a semi-definite cone. So by this, I mean they do exist. They are not something imaginary, they do exist. Okay. So with that, I want to talk about the classical type of optimization problems. As we talked just now, the most basic one is linear programming, which is also called linear optimization. By linear, we mean both the constraints and the objective function. They are all linear. right? They are all linear in X. So that's why it's called linear programming. And so this is linear. What about something nonlinear? And nonlinear, we mean both the objective function f and the constraints could be nonlinear. So here, the function f can be a nonlinear function, and the constraints, the inequality constraint function g and the equality constraint h, all of them can be nonlinear. But when they become nonlinear, the complexity will go up, right? So they will be more difficult to solve than the linear ones. And this is our focus. We just want to focus on nonlinear optimization in this class by using first order method. Another interesting type of optimization, which is also a focus of this class, is stochastic optimization. So you again want to minimize some function f in the set C. But this f is not something very simple. It has the form of expectation. So here, this f is deterministic, but the capital F here is something stochastic. So this f has two arguments, both the discernible x and some randomness c. And this expectation is over c. So capital F here is stochastic, but little f is deterministic. But because expectation means integral in high dimension is intractable. So to solve such optimization is not very easy to do. So we usually do approximations. As I mentioned before, there are two types of approximations, either SAA or SA. SAA means sample average approximation. SA means stochastic approximation. We will talk about more details later. But this is another very important type of optimization we are interested in. And there are many more optimization problems. For example, multi-stage, which is like MDP, Markov decision processes. You have a do not only have one x, but you have x1, x2, x3 in your first stage, second stage, third stage optimization problems. This is more difficult than single stage to solve. And you also have robust optimization. This is some case where, so here, this is the case where you want to minimize some average case, right? Because we are averaging over all the scenarios. C can mean a scenario, some randomness. Here we are like risk neutral. We want to minimize over the average case. But in robust optimization, you are more risk averse. You want to minimize over the worst case scenario. So this will give you a different formulation. And as we mentioned before, like optimization transport or sampling problems, they can be viewed as infinite dimensional optimization problems. Well, these are all in Rn, so these are all finite dimension. So these are possibly the most important type of optimization problems. But I believe there are many more, like for example, distributional robust optimization, which combine these two together, which is much more challenging than these two. But it has many interesting applications in operations research, in economics nowadays. Since we want to talk about first order methods, let's be more specific about what first order means. So basically, this is the question we need to ask. So without giving you the exact formula of f, what kind of access do we have to evaluate f? So first of all, we can assume zero order oracle, which is like if I give you a point x, can this oracle return me the function value at the point x, which is f of x. But this does not mean we know f. It's just a one-point evaluation. So we just know one value of f. We don't know any point, other point in your feasible region C. So this is an oracle. And this is for first zero order. And for first order, suppose I give you a point x. Can you return me the gradient in the smooth case or the subgradient in the non-smooth case? And this is the first order. When we talk about first order method, we are allowed to access to both zero order and first order oracles. So you have the access to everything lower than your current order. So if you want to design a second order method, you have access to zero order, first order, and second order. And these are for the deterministic case. So for a given point x, I can return you either a function value or the gradient or subgradient. This is deterministic. But there are some other oracles, like the stochastic oracles. They can be used in stochastic optimization because we have two arguments, both x and the randomness c. So suppose I give you both the point of interest x and the randomness c. I want you to return me the function value, but this is some stochastic function value, capital F of x and c. And also there is another stochastic variant of the first order oracle.
So the random variable here can also be not real valued.
They're real valued.
They're real valued.
They're real valued.
Okay.
And so this is another. This is an example of the stochastic first order oracle. So I want to return me the gradient at the point x with the randomness c. So these two oracles will be used in the design of stochastic optimization algorithms. And just to give you an idea of what the second order looks like, this is a second order. This is a deterministic second order oracle. So given a point x, I want you to return me the Hessian matrix. So I do not want the function value or the gradient, but I want something high order. That's the Hessian. So if you have, so in our class, basically we will only talk about all the four oracles here. But only in the end, when we talk about second order and high order, we will touch second oracle like Hessian. But before that, we just work with function value and gradient. So with, yeah, this is the claim I just want to make. So with all these oracles, we have a black box model. And the way we quantify the efficiency of a certain algorithm is by counting how many first order oracles have I called, how many zero order oracles have I called. So the numbers the complexity I gave before, like epsilon to the -1/2, this is the number of first oracles I have. So I need to perform this many number of I need to call this number of oracles of the gradient to solve the problem, to find an epsilon solution. Okay. Any questions? Okay, so what does a typical optimization algorithm look like in our class? So
What's the difference between gradient and subgradient?
yeah, this is a good point. We will have a lecture on subgradient. But basically, the difference is the problem you are solving, either smooth or non-smooth. For smooth, for example, like a quadratic function, through each point, you have just one cutting plane, right? And the direction or the slope of the cutting plane is your gradient, right? This is the gradient, the derivative is the slope, right? Or in high dimension, this is the gradient. This is a case where the function is smooth because if it's smooth, there is a unique cutting plane. If it's convex plus smooth. But if it's non-smooth, so here it's smooth. So through this point, you have just one cutting plane. So you still have a gradient. But at this point, your cutting plane could be either this one or this one. So there is no unique gradient, right? And the direction of each line, each cutting plane could be a gradient. And so that's why then they're not called gradient, but they are called subgradients. So for example, in this is f of x equals this is the absolute value. So at the point, at the origin, the point 0, 0, any line here, or even the flat line, the x-axis, could be the cutting plane. So your subgradient, actually your subgradient, usually we use f prime of x to denote the subgradient. This can be anything in this interval, -1 to 1. -1 is this limit, +1 is this limit. So anything in this interval is a subgradient.
So what's the intuition then for using subgradients in the practical applications? Are you trying to drive the iteration to continue to converge? Can you give a sense of Or I'm sure you're gonna get to
So
that
this
lecture,
is-
but I just wanna get a sense.
Basically, we are just mimicking the algorithm that we have for the smooth case. In the smooth case, for example, here, this is a smooth one, right? This is a gradient method. We are using a gradient here. But in the subgradient, you still want to use some first order information at a point xk, but you do not have a unique one. So any subgradient can be a substitute for this gradient. So I just want to replace this one with something meaningful, but it can be anything in this interval. So this is usually typically what optimization algorithms look like. This is the case when we solve convex smooth optimization. We will have a lecture on gradient method. So this is just a screenshot of my lecture. So basically, given a certain step size hk, you want to perform a gradient step. Basically, you take a gradient step at my certain point, my search point xk. I want to go along the negative gradient direction, which is the steepest gradient direction. So in this along this direction minus gradient ffx, okay, I can decrease my function value in the most fastest fashion. So that's why it's called the steepest gradient. So this is a type of iterative method. So this will be a cycle, right? Here's a loop. After performing this step to find from xk, you find xk plus 1, and then you go to the next loop. You choose a new you choose a new step size hk plus 1, and plug into the same formula. You find xk plus 2, and you do this again and again. So after a fixed number of iterations, you output the last point. So this is a typical optimization algorithm. So our goal here is to find the epsilon solution. Like we mentioned before, we are interested in a point x such that the function value is within epsilon distance from your minimizer. Because we cannot find the minimizer by using finite number of iterations algorithms, right? And we can only get an approximate solution. So the way we quantify the approximation is by epsilon. Epsilon is a given tolerance. It can be 10 to the minus 6, 10 to the minus 8, some tolerance that you want. And the search point will satisfy this inequality. And this point x is called an epsilon solution. This is usually used for convex optimization. But for non-convex optimization, usually the objective function could be something very nasty. Like it could be look like this. You may have some local minimum, and this is your global minimum. This is a local maximum. You could also have a saddle point in high dimension. So to avoid, because we cannot guarantee the global minimum, so we are just interested in any point that has a small gradient. So basically means anything that has a flat cutting plane. So all these points could be the epsilon solution. So anything within a small region could be an epsilon solution. So we're just interested in any point that has a small first order information. So, but we cannot guarantee a global minimum. So this is some intrinsic difficulty in non-convex optimization. These are the two typical solutions we want to obtain in optimization. This is for convex, this is for non-convex. Okay.
A priori, in all cases, for the problem, whether the problem is convex or not, or are there some insights? So, if, for example, in practical applications, can you just say, okay, this kind of problem I know because people have solved before, it's going to be non-convex, period, or how do you gauge that without knowing the problem?
Can I determine whether it's convex or
Yes,
non-convex?
exactly. Are there?
For convex, we will talk about the calculus rules for convex functions. For example, like summation of two convex functions or composite function of two convex functions is a convex one, or there's many calculus rules that you can make use of to determine whether your function of interest is convex or not by using all the basic elements of convex functions, right? Like a quadratic function.
In practice, like you go into a company or you're a researcher looking at your problem, and you read all the articles and they tell you all these problems are to first order convex, but you don't believe them?
So there is a way usually that people in practice do is they just believe the problem is convex until some paper they call until guilty, until they have some signal that detect this is a non-convex region. If I do not detect it, I just presume this is convex, and the convex algorithm still applies. This is an interesting idea that has been used in non-convex optimization. We will cover that. There's a very interesting paper on that. So to quantify the complexity of our optimization algorithm, we need to talk about both upper bound and lower bound. Basically, upper bound means upper bound is for an algorithm, and lower bound is for a type of problems. So for a certain optimization algorithm, I want to know what is the worst case complexity that my algorithm has to perform on a certain class of optimization problems. For example, for convex smooth, this is a class of optimization problem. And if I apply a certain algorithm, for example, gradient descent, this is the worst case complexity that I have to do. So I have to do 1 over epsilon iterations of first order oracle evaluation. So I have to do, for example, if your epsilon is 10 to the minus 6, so in principle, I need to do 10 to the 6, so 1 million number of iterations to evaluate the gradient. But this is just on the order of that. There may be a constant, right? So big O notation is something we will use again and again, but we will give a rigorous definition for this one when we talk about complexity analysis later on. And if I apply a different algorithm onto this type of problem, if I use acceleration, then I can obtain a better complexity. So suppose epsilon is again 10 to the minus 6, so my complexity is going to be 1000, right? 10 to the 3. So I will reduce my number of evaluation of gradient information. So this is a benefit of using accelerated method. That's why it's called accelerated. It's much faster. And if you want to consider a different type of different class of algorithm problems, for example, convex non-smooth, like the one we mentioned before, right? Like this absolute value function. So you need to use different algorithms. Suppose I want to use subgradient method, then my complexity is much worse. Is epsilon to the minus 2. And if I use proximal bundle method, so epsilon to the minus 2 is compared with the smooth case. So this means this problem is not good, right? And if I use a different algorithm, proximal bundle method, I also obtain epsilon to the minus 2. So these two algorithms have the same complexity. Complexity is also naturally connected to convergence rate. We will also talk about convergence rate when we analyze an algorithm. So we talk about both convergence rate and the complexity. And all these algorithms here, they have sublinear convergence rate. So for lower bound, this is to describe how difficult my problem is. This is to describe how efficient, upper bound is to describe how efficient my algorithm is, and lower bound is to describe how difficult my problem is to solve. So this is to talk about the least amount of work that a certain algorithm has to do to solve a class of problems. And when we talk about an algorithm, this has to be in a class. So this algorithm has to satisfy certain properties so that they lie in a class. And this is the least amount of work you have to do. So again, let's think about convex smooth problem. People can show the lower complexity bound for this problem, no matter what algorithm you think about, as long as they are in a certain class of algorithms. You have to do this much of operations. You need to evaluate this many iterations of your gradient. And noting that this lower bound matches this upper bound. So this means Nasarov's accelerated method is optimal because lower matches upper. But this one is not optimal because it's larger than the lower bound. There's a gap between them. Well, if you think about convex non-smooth optimization, no matter what algorithm I think about, for example, subgradient and proximal bundle, they are all in a certain class. So just for this class of algorithms, no matter which algorithm I think about, you have to perform this at least this much. You need to do this many access to the oracle. And noting that this lower bound matches both of them. So both of them are optimal. So the optimal just means lower bound matches upper bound. So in optimization complexity analysis, what people usually do is just from two directions. On the one direction, you try to bring down the upper complex bound. This is by designing a better algorithm, like from gradient descent to necessary accelerated gradient. This is a better algorithm design, which brings down the upper complex bound. And on the other hand, you try to push up the lower complexity bound. So when you prove lower complexity bound, you try to find a very bad, an evil instance, an evil function in the class. So for this bad function, no matter which algorithm you choose, you have to perform this many iterations. And your job, your task for lower complexity bound analysis is to find the worst function in the class. So on the other hand, you try to push up the lower complexity bound. So in the end, you want the upper bound to matches the lower complexity bound. This is to close the gap. So this is what Nesterov did to design and analyze this accelerated algorithm. And if time permits, I will also show you how we can show proximal bundle method is optimal. The story is like this. So proximal bundle method was proposed in 1975, and at that time there was no known complexity bound for proximal bundle method. So people just know it will converge in the limit. This is called non-asymptotic convergence. So this is called asymptotic convergence. So in the limit it will converge, but you don't know how many iterations you need to do before convergence. And in 2000. People show that the complexity is epsilon to the -3. So at least this gives us a complexity, but this is not optimal, right? Comparing epsilon to the -3 with the lower bound epsilon to the -2, there is certainly a gap. But the tricky thing is that in practice, proximal bundle method works much better than subgradient method. But subgradient method in theory is optimal, while proximal bundle method at that time was not optimal. So it's very interesting to think about why we cannot show proximal bundle method is not optimal, but well, it's still outperforming subgradient method. Well, in 2021, actually, this is a work by me and my advisor when I was a student. So this is just to tell you a story. So at that time, we were very interested why there is a gap between the upper and the lower bound. Well, by better algorithm design, we show that this is indeed epsilon to the -2, right? So this is just like this is a story for convex non-smooth optimization. This is just like the story in convex smooth optimization. What Nesterov did to close the gap. I think we will have just 2 more minutes. So let's try to cover the development of optimization algorithm. I will talk about the application of optimization in machine learning in the next class. So in the early age, like before 20th century, people do have a certain optimization algorithm, even though we do not have a lot. For example, gradient descent was developed by Cauchy back in the 18th century, and Newton's method has been known for a long time. Because Newton has developed this method for solving nonlinear equations. And this can also be used to solve optimization. Lagrange multiplier was developed to solve constraint optimization by dualizing the constraint. In the 20th century, optimization has gained a lot of development. In the 40s, during World War II, linear programming was extensively used in military applications for scheduling, for programming, for arranging people and operations. And that was the time where operations research was proposed. And these 3 guys are the giants in linear programming. So von Neumann and Kantonovici, they both brought this notion linear programming at that time, and Danzig developed the simplex method for solving linear programming very efficiently. And later on, Kachin and Kamaka did propose more efficient algorithms, ellipsoid method and the interior point methods in the 70s and the 80s, which gave you complexity guarantee and efficient algorithms. So I think it's time to stop now. It's already 10:55. So we will continue next time about the first lecture, the introduction to optimization in machine learning. So thank you very much.
Yeah, I think they've decided that 1 p.m. Fridays are okay, not to be. We can talk about it when you settle in.
So I'm thinking of so all the assignments have been placed all the listed in the syllabus. I think it's 14.
啊，怪不得还记。
净跟研究生一块儿。
Yeah.
So we have yesterday there were 15 people registered. But Blackboard there were 20. Think we need a larger room.
I don't know, but my interest that the first time had the most people and
Oh,
then
yeah.
gradually.
Absolutely.
Yeah, there's some people checking it out.
Yeah.
So you think we need a larger classroom?
No, I mean, I
It's
think
not,
this will
it's not
probably.
increasing, so.
Yeah.
That's not increasing.
Yes. Yeah, I think this is fine unless, it becomes too much, but I think we'll probably have around 20-ish.
Then we are in the good shape.
Yeah. It's a small classroom, but it's intimate, it's nice. I won't be here next week.
You free up one space.
Yeah, I'll free up.
I'm Tolu. Send you the email. Are you settled in?
Not yet.
Welcome. I'll let you settle in. I just want to check in with you that this is me. I'll shoot
Sorry,
you.
I didn't
No,
recognize
it's
you.
okay. Just treat me like a student. Totally treat me like a student. I want to learn. So what will happen is I'll probably shoot you an email because I would love to be able to see the lectures and the resources. I can't register because I'm a.
Oh,
So your TA has to.
I will also put all the lectures on my website.
So
you can see
I
that
can
there.
see it on that website.
For example,
That's okay.
the PowerPoint is also it's already available there.
Gotcha. Sounds good. So whenever you settle in, I'll shoot you an email. We can talk some more.
Sure. I will
There are a couple of interests. A couple of interests of mine with new things happening in psychology, geophysics, and earth science.
Like, exactly, they're so tiny. Everybody's like.
这也太前面了吧！
Energy Society hydrology was not very strong. Energy Society
First try, I got that to work. That's rare.
Yeah.